Hello, can people hear me? Brilliant. Okay, so today we have a guest lecturer. So it is David Vaccaro, and we'll just wait for him to appear. Okay, so it should be recording. David is here. Hello, David.
Hello.
Okay.
Okay, I'm going to share. Oh, can I share my screen?
You should be able to.
Okay, let's try.
Okay. Unfortunately, I've made you host, David, and I can't mute people. So once in a while, so for example, Joe Satchon, can you mute your mic, please?
Okay, well, hopefully I won't need to mute people. I mean, do feel free if I ask questions to unmute yourself. It is quite nice if people contribute. I hope how do people generally find the complex numbers sheet? Because I know that people study complex numbers at different parts of the A-level course. So this might have been an occasion where the sheet was on something which you hadn't seen before. Just put a thumbs up if you were sort of generally kind of confident and happy with the material, or put in the chat areas of the course or areas of the sheet which you might want me to particularly focus on. Oh, we've got lots of thumbs up, which is nice. Okay, I've got a selection of questions. I've got a selection of questions to look at here, and I'll work through a sample of them. The questions I will share with you later, Vlad, and the written work here I will also share. So this first question, let's hope my pen works, which it does. So it says change to polar. It says change to polar form. So this is very similar to what you will do in other areas of maths and physics when you convert Cartesian coordinates to polar coordinates. So the first one, we've got the complex number -I. We consider the modulus and argument of that number. So the modulus is going to be the length of the complex number when considered as a vector. So the modulus of -I is simply 1. The argument is the angle measured anti-clockwise from the real angle, the real axis. So now you could say it was 270 degrees or 3 pi by 2, but the general convention, and I think pretty much everyone is agreed on this, that arguments are between negative pi and pi. So I would regard the argument of negative I as being negative pi over 2. Okay, so we have the modulus and the argument. The question now is, how do we write this complex number in polar form? And I think once you get past a certain point and once you're confident with the notation, the most natural way of writing it is in a complex exponential form. So I would write this as negative I is the modulus, which is 1, multiplied by e to the I of times the argument, so e to the negative I pi over 2, and that would be the modulus argument form. The next questions are relatively routine. The main thing that one needs to consider is the quadrant that one is in. So this complex number, 1/2 take away negative root 3 over 2. We're in the fourth quadrant. And if you know your standard trig ratios, this angle in here is 60 degrees. So the angle is pi over 3, but the argument is negative because we've gone clockwise rather than anti-clockwise. So 1/2 take away root 3 over 2i is the modulus. And again, we can recognize the modulus as 1, or we can use Pythagoras to show that the modulus is 1. And then the arg is negative pi over 3i. I'll just double convince you that the modulus is 1. So the modulus of 1/2 minus root 3 over 2i is the square root of 1/2 squared plus root 3 over 2 all squared, which is the square root of 1/4 plus 3/4, which is the square root of 1, which is 1. Okay, so in this question, the modulus was 1, and the argument was negative pi over 3. Okay, the subsequent questions are similar. You just need to take into account the quadrant. Question number 6. 1 plus I divided by 1 minus I. Does anyone want to suggest 2 possible methods of finding the modulus and argument of this complex number? So we've got this quotient 1 plus I over 1 minus I. Yeah, Edward.
So you can literally divide it by multiplying top and bottom by the complex conjugate of 1 minus I. That's sort of the most obvious way of doing it. But then you can also think, we've already done the modulus and the argument of 1 plus I over. No, but you can easily do that, and you can easily do the modulus and argument of 1 minus I, and then you can just use the rule of dividing the moduli and subtracting the arguments.
Excellent. So you could either, and I think you're right, it's the more naive way of doing it. You could just, okay, that's fine. You could,
but at the same time, other people don't need to hear this.
You could simply do the division, and as Edward said, you would multiply top and bottom by the complex conjugate of the bottom, which is 2i. and then when you multiply the bottom, you get 2, so you get the division is I. And then the modulus would be 1, and the argument would be pi over 2. But in many ways, a equally valid way would be to consider the complex number 1 plus I, which by a simple application of Pythagoras has got modulus root 2 and argument, and by simple trigonometry has got argument pi over 4, 45 degrees. 1 minus I, which also happens to be the complex conjugate, has got argument negative pi over 4 and modulus root 2. And now the modulus of the quotient is the quotient of the moduli, but that's just root 2 over root 2. And because they're, you can also see that because they're complex conjugates, they have the same modulus. And then the argument of the division is the difference in the arguments. So it's pi over 4 take away negative pi over 4, which is pi over 2. Okay, so you can do it either way. You can either just evaluate the complex division, or you can look at the modulus and argument of the individual parts. There's some talk. Do people have questions at this point? Let me just check the chat. So the question, would I say polar form is the same as exponential form? So I think, I don't know what the kind of technical answer to that is. I mean, I think putting it in polar form is thinking of it as a vector defined by its modulus and argument. And the exponential form of a complex number is the most satisfactory and long-term, the most computationally efficient way of representing a complex number using its modulus and argument. Yeah, all good. There's a question here. What property of a vector prevents you from dividing one vector from another? It's a very interesting question, and I think the answer there is that division is a algebraic property, and division is normally defined as the inverse operation of multiplication. So you can only divide by vectors if you've imposed some algebraic structure where you can multiply vectors. Now there are kind of vector multiplications, and you'll probably meet them in your physics and in your pure maths, the dot product and the cross product. But neither of them are invertible. Neither of them are one-to-one mappings. So if you know that A dot B is equal to some number, there's no way you can have a notion of division, because there's very many vectors which, when you dot it with B, would give you 5. In fact, it's a whole plane. So I'd say the main reason why it's not possible to divide by vectors is because you don't have a invertible multiplication operation. I hope that answers your question, Taike. Okay. Is there an answer sheet to the problems on Classroom, or is it marked? I don't know. I don't understand. Okay, I'm going to move on. So question number 1 is done. We've changed into polar form. I'm going to pass over questions number 2 and 3 and concentrate now on question 4. So this drawing in the complex plane. So part I should be bread and butter. If we've got a complex number written in, one could call it Cartesian form or real and imaginary components, you can just read off the real and the imaginary part. So the real part is 3, the imaginary part is -2. So it's simply at the point on a coordinate axis, on a coordinate grid at 3 take away 2i. Okay, so I, it's 3 units across and it's 2 units down. For part II, it's written in polar form, and this time we can read off the modulus as the coefficient of the complex exponential, so that's 4, and the argument as the imaginary exponent, and that is -π/6. So what we've got there is we've got a vector where this angle is π/6 or 30 degrees, and the length is 4. And obviously it kind of goes without saying that you could calculate the real and imaginary parts. You could calculate the real part of the complex number by using the cosine of the argument. So that is 2√3. And you could find the imaginary part of the complex number by looking at the imaginary part, so using the sine of the argument, and that gives me 2. Okay, so this complex number in part II is 2√3 minus 2i. Okay, part III. Can people put into the chat what they think the locus would look like in the case of part III? So it says the modulus of z minus 1. So 1 is the real number, the real number 1, the number which lies on the real line. Z minus 1 is this position of z, it's the difference between z and 1, and we're restricting that the modulus of that is equal to 1. Yeah, so a circle. Okay, so it's a circle of radius 1 centered on the point 1. So it's a circle which goes through which has got center 1, 0 and goes through the origin. So it goes through the origin, it goes through 2, 0, goes through 1, 1 and 1 minus 1. That's part II. The next locus says that the real part of z squared is equal to 4. Any suggestions about the best way to tackle this question? What sort of methodology do you think is the most natural way to tackle question part IV? Well, a locus question involving complex numbers is essentially a locus question of the plane, the Cartesian plane. And I think our intuition, our understanding, our experience is much better, is much more attuned, considering relationships between the x coordinate and the y coordinate that it is visualizing complex numbers. So probably the most natural way to attempt part IV is to consider the complex number as being made by its real and imaginary parts. So let Z be given by x plus IY, where x and y are real. We're invited to find the complex number z squared. So we have z squared is x plus IY, x plus IY. We open the brackets in the normal way, so we pick up a term x squared. We pick up two lots of the mixed term x, y, I. And then when the IY hits the IY, we end up with negative y squared. We can now collect the real terms, which is the x squared minus y squared, and the imaginary terms, which are 2x by I. And we want the real part of z squared, which is this term, x squared minus y squared.
It's a FedEx jet. There's no one on it. It's cargo plane.
Is equal to 4. Okay, so let's consider this locus, x squared minus y squared is equal to 4. So remember that x and y are real. If y is 0, x squared is equal to 4, and x is equal to 2 or negative 2. So there is if y is 0, we have these 2 points with x equals 2 and x equals negative 2. If x was 0, we would have negative y squared equals 4. Now, we're all attuned to complex numbers, and we would want to say that y squared is negative 4 and y is plus or minus 2i. But remember that y is living in the real numbers. So the imaginary value of y is nonsensical. Okay, if y is bigger than 0, then x squared is going to be bigger than 4, and so x is going to be larger than 2 or smaller than negative 2. So the curve exists out in this direction here. Let us also note that if x squared is very large, we have that y squared is equal to x squared minus 4, and the subtraction by 4 asymptotically to a large number is not going to have a large effect. So for large x squared, we can say that y squared is approximately equal to x squared, and we get y is approximately plus or minus x. So we have two oblique asymptotes. And the curve lives in this section to the right of 2 and to the left of negative 2. And so we get a curve that looks like this. Does anyone recognize or want to suggest what curve this is? Yeah, it's a hyperbola. Okay. And because the because the asymptotes are perpendicular to one another, it's what we call a rectangular hyperbola. If you were to rotate the curve by 45 degrees, you would get a curve that was very similar to 1 over x, and I'll leave it as an exercise to see to say what that would be. Okay. Part B, any suggestions in the chat? For what this locus would look like, the argument of z plus 3i is equal to pi over 4. A half line, excellent. If we just ignore the plus 3i for the moment, if we've got argument of z is equal to pi over 4, then we're just back in the polar coordinate world, and we're somewhere on this half line. The fact that we've got the z plus 3i term, if you think of function transformations, that's the same as translating by negative 3i. Okay, so we've got a half line through negative 3i. Question 6 I will leave as an exercise. And question 7 I will leave as an exercise. But let's zoom in on question 8 here. So the argument of z minus 4 over z minus 1 is equal to 3 pi over 2. And I'm going to write it over here. Now, I'm just going to let you into a secret that after we do this question algebraically, I'm going to return to the question and I'm going to think about it in pure geometric terms. So while it might not look like it, okay, this is actually a very familiar piece of geometry. So stare at this relationship long enough and see if you can preempt what curve is going to emerge once we actually do the algebra. So we have got the argument of z minus 4 over z minus 1 is equal to 3 pi over 2. Well, what proved so successful in part IV in terms of doing things algebraically was to rewrite z in terms of its real and imaginary parts. So let us write z equals x plus iy. So our fraction becomes x minus 4 plus iy over x minus 1 plus iy. And we know how to divide complex numbers. We multiply top and bottom by the complex conjugate of the denominator. So the denominator is x minus 1 plus iy. The complex conjugate is x minus 1 minus iy. We know straight away what the denominator is going to be. Well, we could use a difference between two squares, but we know it's going to be the modulus squared. So it's just going to be the real part squared added to the imaginary part squared. When we multiply on the top, we get the two real parts hitting one another. We get the cross terms where the real term parts hit the imaginary terms. And then we get the two imaginary terms hitting one another. So we need to be a little bit careful. IY times negative IY is plus y squared. Okay, and let's simplify everything slightly. So let's gather our real terms and our imaginary terms. So our real terms are these two. So we get x squared minus 5x plus 4 plus y squared. And then our imaginary term, the xy terms cancel, and we've got negative yi, and we're subtracting negative 4iy, so that's the same as adding. So that becomes plus 3iy over x minus 1 squared plus y squared. Okay. Now we want the argument of this complex number to be 3 pi over 2. So let us ask ourselves the question, when is the argument of a complex number (3 pi over 2? So where is that on the Argand diagram? Does anyone want to put into the chat a nice, I was going to say in clear English, but in clear mathematical English, can anyone describe what is meant by a complex number with argument 3 pi over 2? Yeah, so negative, yeah, excellent. A purely negative imaginary number, okay? Because, sorry, the argument is 3 pi over 2. So 3 pi over 2 is 3 right angles. And that takes us to the negative real axis. So this complex number, this fraction, is on the negative real axis. So we've got we can conclude two things. Firstly, that the real part is zero. So x squared minus 5x plus 4 plus y squared is equal to 0. And we can also conclude that 3y, so the coefficient of I is negative. Notice that the denominator is the sum of two squares, so the denominator is definitely positive. So we can also conclude that 3y is negative, which is equivalent to y being negative. Does anyone recognize the type of curve that we've obtained in STAR? Well, it's a quadratic expression in x and a quadratic expression in y, so we can complete the square. on both. So x minus 2.5 squared so x minus 2.5 squared is x squared minus 5x plus 6.25. So to get 6.25, we would need to add 2.25 to both sides. And 2.25 is 1.5 squared. So this is, I've just rewritten star. And we recognize this as a circle with center 2.5 and radius 1.5. So in particular, it goes through the points 1 and 4. And we want y to be negative. We want y to be negative so the locus we want is this part of the circle here. Now, I said at the beginning that we could do this question algebraically, and that's the sort of ugly way, but we could also have thought purely geometrically. Does anyone want to give a geometric account of this relation and explain why this curve is correct? I'll give you a clue. This is a mathematical result that all of you know. So think geometrically about what the argument of z minus 4 divided by z minus 1 represents. And think geometrically about when that argument will be 270 degrees. You might want to stare at the answer. You might want to stare at the fact that we obtained a semicircle to try and get a picture of what's going on. So let's think about the complex number z minus 4. So geometrically, that's this vector. And z minus 1 geometrically is this vector. The relationship that's given in the question is saying that these two vectors are perpendicular. But if I have a point, if I have 2 points, what is the locus of the set of points where the angle between the corresponding vectors is 90 degrees? Yeah, it's a circle theorem. Excellent. Okay, notice carefully. Notice which circle theorem it is. So there's a circle theorem that says that if you have a semicircle, that the angle subtended by a semicircle is 90 degrees. But that's not the circle theorem that's used here. The circle theorem that is used here is the converse to that result, that if you've got a right angle, so if ABC is a right angle, that implies that B lies on the semicircle with diameter AC. So this relationship star is just saying that these two vectors, the z minus 1 and the z minus 4, are perpendicular. And by the converse to the circle theorem, that tells me that they lie on the semicircle. Okay, and then if you think about which one's got a larger argument and which way you turn, you can convince yourself here that you would get the you would only get the lower part of the semicircle. Okay, so this algebra in question number 7, sorry, is not necessarily the way that you would prove it when you first learn it in year 10, but this is in some sense, a proof of that circle theorem. Okay, every teacher's oh yeah, so someone's asked in the chat, so if the argument was pi over 2, would it be the other side of the axis? Yeah, absolutely. Okay, and you can see that because if the argument had been pi over 2, the only thing which would have changed was we would have been taking the positive imaginary axis and y would have been bigger than 0. Okay, this sort of session is every teacher's sort of nightmare, the kind of black screen of faces, and takes everyone sort of back to kind of COVID days. Can I just ask people to take stock at this point, to just put a thumbs up if they're happy with those Locker's questions? If they are, put a thumbs up. If they've got any questions on what we've done so far, then take the opportunity to put them into the chat now. Lots of thumbs up, lots of happy faces. 7:30. Oh, good. Brilliant. Okay, let's move on to a different type of question. I'm just going to create a little bit more space for myself. Pull this down. I'm sure there's better ways of doing this. Okay. What we're going to look at here. What we're going to look at here is we're going to look at the role of complex numbers in solving polynomials. Okay, and the family of polynomials that we're going to look at is the following family. We're going to look at the polynomials x to the 4 plus 1 equals 0, x to the 8 plus 1 equals 0, x to the 16 plus 1 equals 0, and so forth. So which the power of x is going to be 2 to the power n. Now, there's two radically different approaches to solving polynomials of this type. Okay, what are the two different methods or the two different whole ways of thinking about how we're going to approach a polynomial of the type? Well, let's start with this one, x to the 4 plus 1. what two different methods could you use to solve the polynomial x to the 4 plus 1 is equal to 0? Okay, so we've got some really good ideas in the chat. People have said difference of squares, completing the square, factor theorem, quartic formula. That's a good one. Yeah, so everyone here so far has kind of suggested classical approaches to solving a polynomial. Okay, so by a classical approach, I mean difference between two squares, factoring, and so forth. What other approach could you use to solve the, let's write it a different way, x to the 4 equals -1. Yeah, we could plot x in the complex plane. What would happen to the argument of x when we raise it to the power of 4? Well, the argument would quadruple, and we would want the argument of the x to the 4 to be the argument of -1, which is pi. So we'd want an argument of pi over 4. But then we think, the argument of -1 is can not only be thought of as being pi, it could be 3 pi or 5 pi or 7 pi. So the possible arguments of x are pi over 4, 3 pi over 4, 7 pi over 4, 11 pi over 4. Once you get back to 15 pi over 4, you got back to where you start, and you don't get any fundamentally new roots. So we could solve this by thinking of complex, so the two methods are the classical polynomials or the roots of complex numbers, thinking about moduluses and arguments. What we're going to do in this question is we're going to do it the classical way, which is the more involved way. But having solved it the classical way, we'll then think about how we could have solved it using moduluses and arguments, and then we'll end up with a really groovy result at the end. Okay, so that's what we're going to do. So, suggestions for x to the 4 plus 1. Well, people said, I liked people's suggestion of completing the square. So, a complete square that would contain x to the 4 plus 1 is x squared plus 1 all squared. But x squared plus 1 all squared is not x to the 4 plus 1 because it's got the mixed terms 2x squared. So if we want our left-hand side to equal x to the 4 plus 1, we would do x squared plus 1 all squared, but then we'd need to subtract off 2x squared. Why is this useful? What factorization can we do now? Well, this is a square. 2x squared is the same as root 2x all squared. So what we have here is the difference between two squares. So we can factorize as x squared plus root 2x plus 1 and x squared minus root 2x plus 1. Okay, and now we've got two quadratic brackets. Now the two quadratic brackets we can solve by completing the square. So we can write this first one as x plus root 2 over 2 all squared plus a half. And the second one is x minus root 2 over 2 all squared plus a half. Now, at first glance, it looks like we don't have the difference between two squares, but we do have the difference between two squares because we could regard this half as being minus, I'll write it as root 2 over 2 I all squared. And then we can write this as x minus root 2 over 2 all squared minus root 2 over 2i all squared is equal to 0. And now we've got the difference between two squares, we can factorize. So we get x plus root 2 over 2 plus root 2 over 2i times x plus root 2 over 2 minus root 2 over 2i. And then we've got x minus root 2 over 2 plus root 2 over 2i. And then we get x minus root 2 over 2 minus root 2 over 2i is equal to 0. Okay, so what are our four roots? Our four roots are from this bracket minus root 2 over 2 minus root 2 over 2i. From this bracket minus root 2 over 2 plus root 2 over 2i. From this bracket root 2 over 2 minus root 2 over 2i. And from this bracket root 2 over 2 plus root 2 over 2i. Okay, question, where are these 4 points on the Argand diagram? So let's start with this one, even though it's the last one. What's the argument of this complex number? You should just be able to spot the argument by staring at it. Yeah, 45 degrees. We normally, pi by 4. We normally use radians when we look at the arguments of complex numbers. So this one has got argument pi by 4. This one is the complex conjugate. So this one here is the complex conjugate of the first one. So it's got argument negative pi by 4. And then the other two are what you get when you reflect those two roots when you flip the real part. Okay, so the arguments are pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi over 4. Geometrically, that is a square. And you can check that the modulus of each of these complex numbers is 1. Why does that result make perfect sense? What happens when I take the 4th power of this complex number? So if I take the 4th power of this complex number, I just add arguments. So I add the argument pi over 4 times, and that takes me round to -1. So if I take this complex number here, this complex number satisfies z to the 4 is equal to -1. Similarly, if I add 3 pi over 4 to itself 4 times, I get to 3 pi, which is the same as a complex number with an argument of pi, because 3 pi is one complete revolution followed by a pi. So we could have got these 4 numbers using using complex roots. Okay. These two numbers, root 2 over 2 and root 2 over 2, we can think of them as the sine and cosine of pi by 4. So we've proved this very familiar result. Okay, so by solving x to the 4 plus 1 in two different ways, the algebraic solution gives me, we know that the algebraic solution must give me a complex number with our argument pi over 4. And then looking at the real and imaginary parts allows me to get the sine and cosine of pi over 4. That hasn't told me anything new, because we know these are standard, these are our sort of familiar standard trig ratios. But if we could solve z to the 8 plus 1 equals 0, we could get a similar expression for cos pi over 8 and sine pi over 8. Okay, so we've done the first part of the question. We factorized x to the 4 in two quadratics by completing the square. We then solved it by completing the square again. Part B invites me to solve x to the 8 plus 1 equals 0 using a similar method. So what would I do first to solve z to the 8 plus 1? Well, I would complete the square. So z to the 8 plus 1 is z to the 4 plus 1 all squared. Take away 2z to the 4. Which is the same as z to the 4 plus 1 squared. Take away root 2z squared all squared. Which factorizes as z to the 4 plus root 2 z squared plus 1, and z to the 4 minus root 2 z squared plus 1. Let's get with the program. How would I now solve, what method would I use to now solve these two quadratics? How would I solve the quadratic z to the 4 plus root 2 z squared plus 1 in the spirit of the question? Yeah, complete the square again. So this is a really intense question about completing the square and completing the square and completing the square. So let's complete the square again. So we've got z squared plus root 2 over 2 all squared. That gives me the z to the 4 and the root 2z squared. It also gives me, sorry, root 2z plus 1. Sorry, plus root 2 squared. But it also gives me a root 2 over 2. No, it gives me two lots of root 2 over 2 z squared, which I need to take away. So I need to take away I need to take away root 2 z squared no, I'm going to do it differently. I'm going to do z squared plus 1 squared, which gives me a z4 plus 1. It gives me a 2z squared term, which I don't want, but I want a root 2. Z squared. And 2 is bigger than root 2, so I can write this as minus 2 minus root 2 z squared. So this is how I've rewritten that first bracket. The second bracket I can rewrite as z squared plus 1 all squared. And then I need to subtract 2 plus root 2 z squared. Okay. How do I write this as the difference between two squares? Well, this 2 minus root 2 is the same as root 2, the square root of that, all squared. And here I've got the square root of that all squared. So we factorize as z squared plus root 2 minus root 2 z plus 1. Then z squared minus root 2 minus root 2 z plus 1. Then we've got z squared minus root 2 plus root 2 z plus 1. I'll do plus, and then z squared minus root 2 plus root 2 z minus 1. Plus 1. We now want to solve these quadratics. Okay, and I'll just do this last one. And maybe it's safer just to do this last one by the quadratic formula. So we get one solution, which is z equals minus b. So that's root 2 plus root 2 plus or minus the square root of b squared, which is 2 plus root 2 minus 4ac, so minus 4. So that's root 2 minus 2 all over 2. This discriminant is negative, so we can flip the sign and get an I. So we get one root, which is root 2 plus root 2 plus or minus I root 2 minus root 2. All over 2. And then you get similar roots from the other brackets. What do those roots give you? Those roots give you precise expressions for cos pi over 8 and sine pi over 8. And then subsequent roots differing by a quarter pi. What I'll leave as a challenge, because I want to look at some of the later questions, is to generalize to find the roots of x to the 16 plus 1, then x to the 32 plus 1, and so forth. What do you get the feeling that the roots, what do you get the feeling that the roots are going to start looking like? Okay, is lots and lots and lots of nested square roots. Okay, so we've shown that cos pi over 8 is root 2 plus root 2 over 2, and sine pi over 8 is root 2 minus root 2 over 2i. Try and think what expressions for sine pi over 16 would look like, or sine pi over 32 would look like. Okay, and you'll end up with square roots of square roots of square roots of square roots. Okay, question, why would that be cool? If you could get some expression for sine to the pi over 2 to the power n, why would that expression be a nice thing to have? Well, can anyone tell me something that sine pi over 2 to the n is going to be approximately equal to? Well, pi over 2 to the n would become a really, 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 really small angle. And we know by small angle approximations that sine to the pi over 2 to the power n is approximately pi over 2 to the power n. So I'll leave this as a little carrot for you to work on, but you can get an approximate. You can then use this approximation, so this nested square roots, and I can't remember what it looks like. It looks something like this. You can then get an approximation for pi. So pi is going to be approximately 2 to the power n multiplied by some expression involving lots of nested square roots. Okay, and I'll leave that as a challenge to find that expression with square roots and square roots and square roots. As a little tiny bit of an aside, you don't need complex numbers to get that approximation. And in fact, that approximation dates all the way back to Archimedes. But this is a nice way of getting it using polynomials. Okay, I just thought that would be a little bit of fun. Okay, let's move on. Actually, before I move on, can I just double check people are people happy with that last example? Do people have any questions about it before I move on to a de Moivre's theorem question? Okay, I've got an I think so. So what I'll make sure I do, Vlad, is I make sure that I write up this question fully, because I've sort of, in the interest of time, I've only sort of, once I've got to this with the z to the 8 plus 1, once I've got this expression into 4 quadratic brackets, I only found one of the roots. It would have been worthwhile to have found like all of the roots, and then to be clear about why, you know, which of the roots is going to be the sort of principal one, the one with argument pi over 8. And then I'll also write up I'll try and write up the sort of recurrence of the nesting of the square roots. Okay, let's move on to a de Moivre's theorem question. Okay, and I chose this de Moivre's theorem question deliberately. Because it ends up with the same expression for cos pi over 8, which we found using our nested square roots. So I thought it would be neat to see. So use de Moivre's theorem to prove that cos to the 4 theta is this expression. So what is de Moivre's theorem? That would give us a hint how to solve this question. So we start by stating de Moivre's theorem. So we say cos theta plus I sine theta to the power of 4 is equal to cos 4 theta plus I sine 4 theta. So that's an application of de Moivre's theorem. We can open the left using the binomial expansion. So we get a cos to the 4 theta. We then get 4 cos cubed theta multiplied by I sine theta. We then use the next coefficient in Pascal's triangle, which is the 6. And we've got cos squared theta and then I sine theta all squared. Then we've got 4 cos theta and I sine theta all cubed. And then we've got I sine theta to the 4. And this is equal to cos 4 theta plus I sine 4 theta. Let's now try and process the i's. So in this one, we've just got an I term. So we've got 4 cos cubed theta sine theta I. Here we've got an I squared term, and I squared is -1. So we get minus cos squared theta sine squared theta. Here we've got an I cubed, well, 2 of the i's make a -1, and the third I makes a -I. So we get 4 cos theta sine cubed theta I. And then finally, an I to the 4 is I squared, which is -1 squared, which is +1. So we get a sine to the 4 theta is equal to cos 4 theta plus I sine 4 theta. So what identity can we write down for, oh, sorry, yeah, so question in the chat, would we be asked to solve something like z to the 8 plus 1 equals 0 in our A-level further maths exam, or is this just for extra knowledge? You wouldn't be asked to solve something like z to the 8 plus 1 equals 0 in an A-level further maths exam, but that pattern of completing the square, using the difference between two squares, getting the nested square roots, and making the leap between solving z to the 4 plus 1 equals 0 and then z to the 8 plus 1 equals 0, I could really imagine a step paper asking a question like that. Okay, so let's look at where we've reached with this de Moivre's theorem. The question is inviting us to get a expression for cos 4 theta. So using this expression here, what can I say that cos 4 theta is equal to? Which terms on the left do I need to pick out? Well, the cos 4 theta is the real part on the left, so I just need to look at the terms on the left, which will be real. And so these are the first term, which is cos to the 4 theta. This middle term, which is 6 cos squared theta sine squared theta. And then this final term, which is sine to the 4 theta. What is different about this expression that I've obtained, the cos 4 theta minus 6 cos squared theta sine squared theta, and the target identity, 8 cos 4 theta minus 8 cos squared theta plus 1? What do I have that I don't want? So there's been a question in the chat. Can you always separate the real and non-real stuff? Yeah. So if two complex numbers are equal, then their real part and their imaginary parts are equal. Okay. And so because I know that 4 cos cube theta sine theta I, the terms with the I are pure imaginary, they must be the terms which are making the imaginary part sine 4 theta. But what people have pointed out is that I haven't got the identity I want because I've got these sine terms. But which identity can I use to get rid of sine? Well, I know that sine squared theta is 1 minus cos squared theta. And if I want to make sine 4 theta, I can just make 1 minus cos squared theta all squared. Okay, so let's now simplify. So we get cos 4 theta minus 6 cos squared theta plus 6 cos 4 theta plus 1 minus 2 cos squared theta plus cos 4 theta. And then when I combine the cos 4 theta terms, I get 8 of them. When I combine the cos squared theta term, I get negative 8 cos squared theta, and then I get plus 1. Okay. It now says deduce that cos to the pi over 8 is this. Well, cos of 4 times pi over 8 is the same as cos of pi over 2, which is 0. So if theta equals pi over 2, sorry, if theta equals pi over 8, then cos 4 theta is 0. So if theta equals pi over 8, cos 4 theta equals 0, which implies that cos 8 cos 4 theta minus 8 cos squared theta plus 1 is equal to 0. But what we have here is a quadratic in cos squared theta, which I can solve using the quadratic formula. So I've got cos squared theta is equal to 8 plus or minus the square root of 8 squared, which is 64, minus 4 times 8, which is minus 32, all over 16, which is then 8 plus or minus the square root of 32 over 16. The square root of 32 is the same as 4 root 2. And then if I divide top and bottom by 4, I get 2 plus root 2 over 4. So cos squared, sorry, plus or minus. So cos squared theta is 2 plus or minus root 2 over 4. And so cos theta is plus or minus the square root of 2 plus or minus root 2 over 4. Okay, so we know that cos pi over 8 is one of the 8 possible arrangements of the plus or minus sign. Okay, so now which one of them is going to be cos of pi over 8. So what we've really solved is we've really solved for the values of theta when cos 4 theta equals 0. But if cos 4 theta equals 0, that means that 4 theta equals pi over 2, or some complete revolution added to pi over 2, or minus pi over 2 plus some whole revolution. So the values of theta when cos 4 theta is 0 is pi over 8 plus n pi over 2, or minus pi over 8 plus n pi over 2, which gives me values of theta which are pi over 8, 5 pi over 8, 9 pi over 8, or 13 pi over 8, minus pi over 8, 3 pi over 8, 7 pi over 8, 11 pi over 8, and to make them all positive, I'll take 15 pi over 8. Okay, but we can see this 15 pi over, cos of 15 pi over 8 is just going to be the same as cos of pi over 8. So these are just the negative angles. So these don't give me different values. So these four roots correspond to cos pi over 8, cos 3 pi over 8, cos 5 pi over 8, and cos 7 pi over 8. Now, which is which? If you think of the largest cos graph, if you think of the cos graph, the largest positive one is going to be cos pi over 8, because the smallest angle is going to give me the largest value of cosine. So cos pi over 8 is the largest value. Cos 3 pi over 8 is going to give me the smaller positive value, which is 2 minus root 2 over 8. Cos 5 pi over 8 is going to give me the negative of cos 3 pi over 8. And cos 7 pi over 8 is going to give me the negative of cos pi over 8. Okay, now I haven't given every single detail. But if you look back at the previous question, you should notice that these nested square roots with 2's and root 2's, and sometimes with positive signs and sometimes with negative signs, were the same terms that we were getting out when we solved z to the 8 plus 1 equals 0 using repeated completing of the squares. Okay, so this question really complements the previous one, and also points to the fact that if you were to complete the process, you would get a similar expression for cos pi over 16. Okay, which would be some further nesting of this square root. Okay, and I'll leave that as an exercise. Okay, so what's the moral of this question? So de Moivre's theorem allowed me to get an expression for cos 4 theta. The expression for cos 4 theta initially included even powers of cosine and even powers of cosine and even powers of sine, but the even powers of sine we could turn into cosines using the identity sine squared theta is 1 minus cos squared theta. That enabled me to express cos 4 theta as a polynomial in cos theta. And so solving the equation cos 4 theta equals 0, you can solve it, you can find the angles using classical trigonometry. But you could find the values of cosine by solving the polynomial. Okay. And I think this exactly the same thing is going on here. It was going on in the previous question, where we could solve a polynomial. We could solve a polynomial x to the 4 plus 1 algebraically to get the roots, or we could solve it by getting the complex roots of, in this case, -1. Okay, any questions about those two examples? Okay, super. So let's finish with a step 2 problem. Where's my step problem gone? I think I might have deleted it in error. Wait a second. Ah. Okay, so oh. Yeah. Sorry, everybody. I've lost the last question, which I was going to go through, which is the which was a step problem on complex numbers. Ah, it's a shame. It was a nice one. I will dig it out and I will put it onto the I'll put it onto the list. I'll put it onto the list of questions to look at. But we're almost at 7:30, so I think that's pretty much out of time for the webinar. Does anyone have any final questions before we wrap up? I'm going to stop sharing.
Is there a particular reason why z to the 8 leads to giving a value for signing cos?
Say again?
Is there a particular reason for z to the 8 plus 1 leading to values of signing cos?
Yeah. Let me show you. Actually, let me show you what Archimedes did, and then I think it'll we'll see what's really happening. So we know that cos to the pi over 4 is equal to root 2 over 2. If we wanted to get an expression for cos to the pi over 8, we can use the double angle formula. So we can use cos 2 theta is equal to 2 cos squared theta minus 1. So if we apply this to pi over 4, we get cos to the pi over 4 is 2 cos squared pi over 8 minus 1. But then if we use the value of cos to the pi over 4, we get root 2 over 2 is equal to 2 cos squared pi over 8 minus 1. So then we get root 2 plus 2 over 2 is equal to 2 cos squared pi over 8. And then we get cos squared pi over 8 is equal to root 2 plus 2 over 4. And so cos pi over 8 is the square root of root 2 plus 2 over 4. But if we do the double angle formula again, that is equal to 2 times cos squared pi over 16 take away 1. So we can say that cos squared pi over 16 is this square root plus 1 all over 2 and then square rooted. And then if you just sorry, so you get this nested, square root, you get this nested square rooting. So the double angle formula would have led to this nested square rooting quicker. And then obviously you can get sine pi over 16 as being the square root of 1 minus cos squared pi over 16. And this cos squared just takes out one of the square roots from that nesting, and then you put it inside a new square root. So you can get nice expressions for sine pi over 16. By nice, I mean complicated nested square roots, which are difficult to write down. But you can get expressions for sine pi over 16, sine pi over 32, sine pi over 64, which in what Archimedes was doing was he was finding the perimeter of a square and then a polygon with twice as many sides, and a polygon with twice as many sides, and a polygon with twice as many sides, and then approximating that to the circumference of the circle.
Now I need to learn the double angle formula. Is that even covered in Maths A level?
Which formula?
Is the double angle formula covered in A level? Is that
double angle. Double angle formula is covered in single Maths A level. The double angle formula we could quite easily prove now by De Moivre's theorem. because we could just do cos theta plus I sine theta squared, which is cos squared theta minus sine squared theta plus 2I cos theta sine theta. But then de Moivre tells us that this real part is cos 2 theta, and that this imaginary part is sine 2 theta I. So we have cos 2 theta is cos squared theta minus sine squared theta, and sine 2 theta is 2 cos theta sine theta.
Okay. I'll need to reflect on it now to embed it in my head. But thank you. That helps.
Yeah, it's quite. I mean, I think it is really I think it is something that you should reflect on, because you could prove these double angle formulas completely geometrically by looking at the sort of geometry of the circle or something like that. And it's quite cool that there's a completely algebraic way of proving them. You know, so a computer would be completely adept at proving trig identities now in a way it wouldn't have been before complex numbers, because a computer you can't really envisage a computer doing the geometry, but you can envisage a computer just processing, you know, just algebraically expressions involving, you know,
yeah,
the complex exponentials. So complex numbers, amongst many other things, is a way of turning geometry into algebra.
Yeah, I'm aware of that.
Which is kind of cool.
Yeah, for me to fully comprehend it, I just need to think about it for a while. I've not like touched any of this in the past, so I need to put probably a few hours in to fully get it.
Yeah, I think that's in many ways that's music to my ears, because I think that's the point of, you know, this webinar. In some sense, the point of the whole program is it's getting you wrestling with concepts and hopefully making you think that that's something to look forward to, because this is very much the flavor of university maths.
Oh yeah, I plan to do computer science, but so this is, well, actually no, this is related. I know for sure it will be.
Yeah, I think so, because I think that
exponentials,
you know,
I know exponentials are used, well, imaginary ones. I know they're used in the matrices in some way.
Yeah, well, exactly. It's the same sort of thing. Like if you're going to do computer science and you're going to do geometry, and let's say you want to do some visual processing and you want to understand rotations and reflections and stuff like that. Yeah. The easiest way to code it is if you can code it into something algebraic, and at least in 2 dimensions, that's what complex numbers do for you. Yeah. And in 3 dimensions, that's what matrices do for you.
Yeah. I need to do a bit of research for that then.
I think that would be a good idea. Yeah, if you have any questions and if you want any guidance in your research, I'm sure you can contact me via Vlad or.
One thing is, can you upload all of your working on these questions? Because I feel like all of that will be helpful.
Yeah. And I think I might, especially with the z to the 2n+1, which I probably bit a little bit off more than I could chew in terms of writing it up nicely. I'll try and find time to really write it neatly. You know, so I think it'd be a good exercise to go away and see if you can make sense of what I did tonight, but then also to have a look at the neat solution to try and get a general solution for z to the 2n+1 = 0 with all the nested square roots nicely.
All right, thank you.
I've not had dinner, so I think I'm starving. So I think I'm going to call it a night at this point, but hopefully see you again soon for another maths one.
Yeah.
Thank you very much, David.
You're welcome, Vlad.
Thank you.
Goodbye.
Okay, bye-bye, everybody.